Guys, I welcome you to our next lecture.
Guten Morgen. Guten Morgen.
Guten Morgen. So, let's have a look in the online chat if somebody is coming from there and watching too. Why does ask after a login? I don't want that. Okay, I log me in. Ah, crosswalk. Where's the crosswalk? I think this is the crosswalk. Traffic lights. You know these questions are coming from Google to verify I'm not a machine. So, okay, we go on. I think about that next week. I think next week is the first week in December. So next Friday, it's December the 4th. It should be worth to present you your exercise tasks for this mobile computing course here, so that you can get in charge and plan how to make your attestation for this semester in mobile computing, and that you can start and have enough time for doing things on your own. So that's my idea, to give you the tasks, the exercise tasks next week, and then you can decide if you want to do version A or B. I think I give you at least two different approaches. They are quite similar, only the content is differs a little bit, and you will see it next week. So we do this next week. Today we go on with Kotlin. We are quite fast in talking about things in Kotlin, so we are already in the object-oriented part. This is, I think this is part 2, and the last part, this is some specialties. So we are over the half, or we are at the half of this Kotlin part, so that if we finish it in the next 2 weeks maybe, then we can concentrate on the Android part at 100%. No. So let's go on. We have talked about classes and objects, and we have seen that we can declare classes very simple. We have the keyword class. You know that from several languages. And oh, we lost somebody. I hope he's coming back soon. So we have the keyword class, and therefore we can declare classes. Very simple. Just use the keyword and give it a name. Then we are already going with a class. So this is a simple approach, having a really simple class A, and if we print it, we get an object of this class. We don't have the need to write the new keyword for creating a object. It is just created if we write the class name and the braces. This gives the compiler the advice, okay, we want to call a constructor here. Find out if you have a constructor to construct an A, and if we do not apply anything, you know there will be a standard constructor there which is constructing objects of this type. Since this type is really empty, this will be a very small object. Just have a reference to some minimal space, and we have it. If we play it, we see this is similar to Java. You see we produce Java code, and what we see in effect is a Java object, which is of the type A, and that's a hash code for the entire object here. So really simple, but now we want to produce some more specific things into this. We want to have a class body, we want to have some attributes, and we want to construct classes with parameters. And that's why we have a closer look at this object construction way. There's one kind of constructor. It uses the keyword constructor, and let's see. We can have a class body, and we can have the keyword constructor, which is constructing this class. So this is a simple approach, having a simple class and a standard constructor without any body. Let's try if this works, and it works as the same. So this is the same as we had in the version before, but we just gave a constructor here, and it does not need, there's not the need to have the name of the class. So this would be here an error, because you see this is the same expression like this expression, and that's why we can't use this class name to say this is a constructor. It must be a different thing. So we want to write this in code, then we may not write this in the, that's why we have to write another keyword. Okay, but we're still fine, because, and we have two different kinds of constructors. We have primary and secondary. A primary constructor is the first constructor you have. It's primary. We can have several another constructor could be here, but now we have the twice the same. So the compiler says, no, you have two constructors with the same parameters, not possible. Make another, make anything else, make a maybe a name, a value here. So now we have two destructors, and this one here is the primary, and this one is the secondary. Why should this be the primary? Who is the primary constructor? This is now the question. Let's see at the warnings. Constructor is never used, parameter name is never used. So who is the primary constructor? So which one is primary? The secondary is always delegating to the primary. So if we say this is a value, now this is a primary constructor, but this is the second constructor here. So the primary constructor might be this one. So if we change the order, this one gets the, no, it's the secondary. So it's always the secondary. Okay, the special constructor will always be the secondary. So this will be automatically the primary, whether or not the order is not recognized here. So we can change the order, but it does not change anything, because this attribute is not working. So this C.Schaller decides this one is our primary constructor, and we have to delegate the secondary to the primary, and this is made automatically. You know that this keyword we can delegate to the primary constructor with this keyword here, and we have to. So if we don't need any parameters, that's what we get automatically. We can construct the A with the primary constructor now, and we can construct it with the secondary, give any name. So if we want to see the difference, we just append some code and say print here the word primary, and here print the word secondary. Now it should print secondary here in this case, and we see it prints both. So the primary constructor is always used. If I take this away, the primary constructor should be called. Is not called. Okay, it's not called. So this time it's not called. Okay. This one is now called, and if I use print A, so both are secondary. This is not primary. This is also secondary. This was my fault. This is secondary 1 and secondary 2. A primary constructor is written outside the function body. The primary constructor is this one. This is a primary constructor, and now you see the difference. And here we have now the fault, and that's why I wanted to show you that. Now we have to delegate to primary constructor. This is a primary constructor following directly the class's declaration here before the class's body begins. Yeah, that's called a primary constructor. And this is a second can have several of that. I can have only one primary constructor, so this can be only one. I can write this only once. And here in the function body I can have several more constructors, and they all have to delegate to the primary constructor. So in my version before there were 2 secondary ones. This here is the primary one. So if you want to know where is the function body of the primary constructor, there is no direct function body. The function body of the primary constructor are those init blocks. We can have init blocks, and those are then primarily called. So here I have a init block. This init block is called. I make print lines. Maybe it's better to use print line so that you can read what is coming out. I make some lines in between. So we have a primary for the primary constructor. Okay, let's make print line out there. Better to do this. This constructor here is always called. The primary constructor has always to be called. If we have a secondary, this secondary constructor must delegate to the primary constructor. That's why if we use the secondary, the primary is called as well. So we see primary is the first approach here, just using this primary constructor, and the secondary one, if we use it, the primary is called through the delegation here, and we have always used this primary one. Okay, this is one thing. We can have several init blocks. Both are called always before the secondary. So primary, primary, secondary is now the order. Both init blocks are called, and then the secondary block is called. So if we use this, it will happen that the primary constructor is called, the object is constructed, all init blocks are called in the direction we call it. So if we have here primary and primary tick, this tick will be the second one, the second init block, and if we change the order, the tick block will be the first that we call. So this direction is going from beginning of the class to the end, and the init blocks are called in the order they are written in the class. Okay, several secondary constructors can be placed somewhere in the body, but they all have to be they may not be the same. So you see, it's the compiler can't decide which one to call. We have to give other parameters here, maybe a surname as a string as well. Now we have a constructor with 2 parameters, and we can have secondary 1 and secondary 2. We have 3 constructors at the moment: the primary one and the secondaries, which delegate to the primary. Here I can delegate to the secondary 2. Those can delegate to each other, and if we use this maybe John Doe now. Okay, that's why secondary 2 now delegates to secondary 1, and this one delegates to the primary, which uses both init blocks. So I clear out this one init block. You have seen we can have several ones. The init block is normally the special body of a default constructor of a primary constructor. So this is part of the body of the primary constructor. And they have their own bodies, so they do not use this init. We have no secondary inits, so just for private primary construction, the init blocks are used. Have you any questions so far? Now we want to be... Yes, please ask.
Okay, so is there like are there cases when developing with Kotlin? Are there cases where would we like implementations of using primary and secondary constructors come into play, or is just a concept that you can actually use, but is it being used? Like, is it something that is very practical in Android development for Kotlin? So I just wanted to.
So in the primary constructor is very common here. So normally you don't really need more than one constructor, because you have those standard parameters. We have named parameters, and we can have them with standard values here. So if we form a good primary constructor, it is normally not needed to have some secondary ones, but it's possible. Yeah, I just want to give you the chance to see. Okay, I can have my this stuff as I know it from Java, maybe. So if you want to say, okay, I don't like this, it is too abstract, I don't like it, I can leave it out, and then it's the same for the Java programmer as it was, just have the word constructor. But this part is still called, the primary part here is still called. There will always be a primary constructor.
Okay.
Yeah. Okay. This one is still called, but we can't use, if we don't write one, we can now not use this. If I take this out, it's like in Java. If I don't define an own constructor, I get some generated version. If I define an own constructor, there's no default version generated, so I can't use this default version here. But if I leave it out, the init blocks still get called. So this primary init will still be run through. Yeah. Now I have this, they do not delegate, I have several constructors, and if I come with my Java version of my class, I can write a code which is directly mapped into a class which looks like a standard Java class. Yeah. Okay.
Understood. Thank you, Paul.
Thank you. You're welcome. Good. But we will focus a little more onto this primary construction because it's a little bit new. And the secondary part is a nice to have here. So let's focus on this primary construction. Since there is the primary constructor always here in this position, we don't have the need to write the keyword constructor, only if we want to annotate it with something else, maybe a annotation or maybe a modifier like private here. So if we have a class with a private constructor, we may never construct this class. So this is a class with a private constructor. We have never a chance to create any object because the constructor is private. Yeah. A class with a private object, the class is existing. If we make it open, we can derive from this class, and we can have subclasses which are able to be created, objects from subclasses could be created, but this class objects can never be created because the constructor is private. You know this problem in object-oriented languages. You can have it in combination with abstract classes. Sometimes abstract classes normally can be constructed in a subclass, because the subclass has to rewrite the abstract methods, and in subclasses you can have access to private constructors too, but outside of those classes you can't construct. You have access to protected members but not to private ones, so in subclasses you aren't able to construct a base class object in case of abstract classes and derivation or extension. But maybe we make such a example later. We go back to a normal approach. We want to have a constructor, and if we don't need this special keywords here, if we don't need any annotations here, we can leave the constructor keyword out. And what we get is something we know already. This looks like a constructor declaration as you know it from Java or other languages, and this seems to be the same like down here. So if the class keyword is before this code, it means this is the definition of a primary constructor here, and if there is no class keyword, it means it is the construction of a new object using the primary constructor, or using any constructor, and if it matches the primary one, then the primary one is used. So now we have a primary constructor. We can write something in there. Maybe I give this object of the class here a name. You know, we have default values. Possible we could call the default object name name. So this name is now just a parameter. How to bring this parameter into the class now? We would write a property. Maybe we take a simple property, a variable, which is also called name, or let's call it a little bit other. Let's call it given name. Given name is a string and is initialized with name. This is possible in Kotlin. We don't have a special body for this constructor. The body is the same as the class's body, and that's why we can simply do this here, and this value we write here is coming from there. You know this in Java 2. In Java 2 we could write here something like Mary. We can write it because if we create the object, this code will be evaluated, and the string, the given name attribute, will have a value. Then comes the constructor, and the constructor can replace the value with anything you want to produce for a standard construction or a special construction here. And what if we combine those two features? So the Java way would be write a constructor, take a parameter here. So go back from the primary one. I take the primary one away. Okay, so we just have a secondary one. Take this in, and then we would write, you know, name or given name is name. You know this, it's not a problem. This is the Java approach. You know, so we would write it in Java like this, and then we can create an A object here with a name. We can leave the name out because this parameter has a standard value. That's why it does not, the compiler is not angry, or the IntelliJ is not marking me this code as wrong. So if I give here the name John, we will actually see John in the value field given name. So you see, I give the name John. John is coming here. In here, John will be set into this variable, and it will be saved in this memory here, and we can access it with the point access operator, and then we just write the attribute name, so you know the same things in Java 2. I guess, I'm sure. Okay, now we make it a little bit harder, step by step. What if we have this attribute called name? So now we should change this into name, but you all know, hey, the solution is this pointer. If we use this pointer here, this name, and we can have the difference, that's the name in the memory in the object. This is the attribute access now, and this is this name. Because of this name's scope is only the constructor here, it's the scope of the local variable name, and this is here a variable out of this scope, so we have to use the this pointer, and our program will work again. Okay, now let's think about a primary constructor. This is the Java version, and we want to have a cool Kotlin version now. So let's take that. Now we have the problem that this code isn't run. We could say, okay, make an init block. Yeah, make an init block, and then you can use it. And that's what I said. That's what I already mentioned. This init block is part of the body of the primary constructor. That's why we have access to the attributes given in the primary constructor's parameter list. We have access to them. So this is the local name, and this is the name in the object. Program should be the same. So you see John. Yeah? Not Joe and not Mary. But now, if we change this, the variable is never there. So this attribute is not in memory. It's not available. It's not declared. We can't access name in the object, because when this initial block is run, this variable is not yet in memory. It's not yet an attribute of the class's object. So this init block has to be after the attribute definition here. You have seen this. Yeah? You have seen the compiler knows it. We have no access to this attribute because this attribute is not defined on line 4. It is defined on line 5 and after line 5. So there is a order. We can mix the variable or attribute definitions or declarations and the init blocks, and the order is implicitly given through if I want to access a attribute and initialize it with a value, I should do this after the variable declaration. Then it works fine. Okay, comes after this. So, next step. The compiler is very clever. So, the string Mary is never used. This string Mary is always rewritten either with the value I've given here, from here, or with the value I have here. So if I leave this value out, my standard version is called, the name is set to Joe, and this name is written into the object, and I might see Joe when it's printed out. So we see now Joe. So Mary is never seen. We can't make it that we see the string Mary. It's never seen. So that's why the compiler is very clever. We can write this like this. So just write it like that. Next step. We evaluate it step by step. This is the next step. So what is now the problem? I don't have to write this. I can't write this here on the left. So I can't write this. It is just the declaration of a new attribute, and we give this attribute a name in the declaration, and the compiler says, okay, this is no problem for me. So have you ever seen this kind of code? In Java maybe it wouldn't work. It won't work in Java. We declare a variable in this scope and use the same name on the right side of the assignment. Not possible in other languages, but in Kotlin. So now we have the final, almost the final version of our product. So it is Mary, we have never seen Mary. Now we see Joe, or if we want to see John, we just write here John, and then we see John. We have always, it's still the same version of our class. So the outcome after construction of this object is always has always been the same. But the steps in between were a little bit different, and now we make it much easier in reading and understanding. So what if I say this is name and this is name? Why can't I combine? Why don't we can we leave this out? So what is missing here to make this one to that one? It's only the keyword variable. So you see, it's only the keyword variable what's missing. So let's write the keyword variable here. And Kotlin knows this should be a attribute with the name, and it should get the value Joe, or it should get the value the programmer decided to give into this primary constructor. And that's why the program is still running. So we have still a attribute called name, and it's accessible for us. We don't have it private somehow, so we can access this attribute, and we can set it via the primary constructor with a value. We can set it to John, or if we leave it out, we have the standard version, set it to Joe. Now we have the Joe version, and both is possible. And this is really fine, I think. This is really fine. So this line, this simple line says, we don't need these braces anymore. Can leave them out. So this simple line says, create a class. This describes a class with one single attribute. Name is type of type string with a standard value Joe if we don't give one, and if we give another one, it will be the other one. That's all. And then we become those objects. Really fine. This is what the primary constructor is for. We can give this keyword just in the primary constructor. So only the primary constructor is able to have this approach of I write variable or value. If I write value, it's always is true as well. So I can access this attribute, but just for reading. Just for reading. And yeah, this is very interesting because this is a getter method. It accesses the getter method. We will talk about properties on the next slide, I think. Oh no, 2 slides more. So on some slide today we will especially talk about the properties and the access methods especially. Have you any questions now? So just to repeat it in short again, if we have a primary constructor like this one, we could have some more constructors, secondary ones, and the secondary constructor has to delegate to the primary constructor, and we could say Mary. So now this secondary constructor here delegates to the primary one. The primary one is always the only one up here. And if we have more than one constructor, maybe we now have a secondary constructor, a standard constructor. So the standard version is not more the Joe version. Now the standard version is the Mary version. Oh, it's quite nice.
Also, we don't have to use getter setter methods here.
That's right. In code, when we just write down we want to access this attribute, and the compiler says, okay, you access the getter method. So the compiler makes us accessing a method here. We just write the name of the attribute we want to read, and the compiler knows, okay, you want to read this attribute, so you have to access the getter method. And if we want to write this attribute, he generates code which accesses the setter method. This is why this is a little bit complicated, and I think I show you if we have a variable z, maybe has the value 4, and if I have the variable y, I can't have the y variable. I can't have the y z plus plus. Yes, but moment. Z plus equal 3. This is a problem here. So we can code. There is code generated if we change an object value. The object. This is an object. You know this is an object of type int. You don't see it because you maybe are. You maybe, if you program Java, if you have primitive data types in C++ or Java, you don't actually recognize that this is a real object. And if I have a real object, then the attributes should be private. I shouldn't access the attributes directly. I should use methods. And that's why this here will be change the value, get the old value, append the new value, and then use the set method. So it should be z plus get value plus that z dot get value plus 3, and this should be the new value of z, so z plus set value, this one. And this is a void method. And that's why this expression here does not give a value. It's not giving a value. Should be something like, yeah, it's always using methods. You are always using methods here if you change some things and you don't get a value back in those expressions, like we would get it with the primitive data types in other languages. Yeah, we have to do it in our case like that, because this is something like an expression which gives void back, gives nothing back. Yeah. And therefore the compiler generates, if we say okay, this must be read access, it generates the getter method. Yeah, makes the getter method run here, call here.
Mm-hmm.
A method call is generated for the getter method, and if we write something into this variable, the setter method is used. But we come back to this. Come back to it later. So we show you it now. At the moment, I can show you. A is jolly. A plus name. A dot name is jolly. Now I can access jolly. So the first A now as jolly. For us, we think, okay, this is just a assignment, but no, that's not a assignment. It is a setter method call. That's why we have a void approach. We can't assign this has no return value. It's void because it's using the setter method. But more of that later on. Now we are still thinking about classes and construction. And if we write this in the primary constructor, we get a attribute generated in our class. Okay, this was the construction. Maybe we must make another funny thing. You know the fun to string function, and then we return the string version, just the name. So the toString function should be of type string. And we have to override it because this function is part of the object class. So we override it. It is a keyword, but you already know in Java you write at override maybe to
Assign.
yeah, you write this annotation in Java. You like maybe you like it to say, okay, this should be a overridden method. If not, this would be an error. So you mark this override, and here we have a keyword to say this is a overridden method, and now we can just print the object and we get the name. But we can still make it better, so this is not the last word in Kotlin. In Kotlin we have, I want to remove this return because the last statement should be the return, and we have it more easy in functions. We can't leave the return out. So if I leave the return, this is an error because it's a function body. It's a function body, but we have the assignment. We can have a assignment for functions. And since we have a assignment for functions, the return type is obsolete. We can leave it. And this is now the toString version of our function.
Very interesting.
Yeah, this is very interesting. But we come back to this on another slide again. So just a little look into what is possible. We come back here. Good. Okay. Next slide. What can be class members? We have seen we can have attributes. The attributes can be defined in the primary constructor already, so they are generated into our class. We have in the class several secondary constructors and initializer blocks. The initializer blocks are part of the body of the primary constructor, if you want to see this like that, because they are always called when the class's objects are built in memory. We can have functions, so functions or methods. Yeah, I say functions because the keyword is fun, but if we write those functions into classes, those are called methods. It are class members, functions or methods. We have properties. We can write our own properties more than the primary constructor is using or is initializing, maybe. And we can have inner classes, and we can have object declarations. So make a example to that. What is a object declaration? What is a inner class? We make some examples to that now, step by step, and then we go on with inheritance. So extending classes. We have our class A. We have the one name here, and I leave this constructor maybe out now. Let's make another variable. The surname should be a string as well, and initially it should be empty, and the init block gives it a value, maybe is utter. So this could be, or rewrite this utter down up here. So okay, why not? Now we have a class with two properties. This property here is never accessed because in this code where we use the A, we never access this property. To access this property, we could give it back as string here, and you know this notation, name $surname is now doing the work. Now we access the surname, and the IntelliJ sees, okay, used variable. Now it's a used attribute because we use it here, at least in this function, and that's why it is now in another color. We get both names out here. Okay, this is a property. We can have a inner class, or maybe at first the object declaration. We can have objects directly in here, and the object should be a maybe this is a object inside the class in this way. In this object we can write down several things, maybe another value, number, int value 10. So what to do with, I want to see, I want to have a look in the stream, but what to do with such an object expression here. We therefore have a moment. This is just a pardon, I did not use it for a long time. That's why this is a singleton object in this case, and it's called an object declaration, and it has always this object keyword. Therefore, yeah, and can we use it in a variable? That would be what would be the variable if we write it there. Okay, I can't use it in this case here. So now I have a attribute which is a object and has a number, and I can access it. It's similar like in JavaScript, so we can access the values here over v plus, and we have the number. Maybe? No? Let's see what is in there. What is in there now? So it's in an inner object here. We have the type is a dollar. It's an inner class created, and it has no type at the moment. A other thing would be a companion object. We could give this object a keyword companion, and if it has no name, it is anonymous, and if it has a name, we can access it like the name given. So this is the object's name here. Okay, this is the object's name. Maybe we have access to the object's name like this, and we have now access to this object. You see, this is a name of a object. I should write it with a small letter maybe, and then we have access to this object. It's just the object expression here. Create a object called C, and this object can be accessed with this name, C name, and we can access the value like this. This is a object expression. For what is it useful? Those objects could be derived. So useful in case of derivation. Of other classes or interfaces. Of other classes or interfaces. So it just generates an object here, and another thing should be this companion object, but to the companion object we come back later. it's a special kind of object. There's another keyword called companion. Companion is maybe a is it French? What do you think? Is it a companion? You know it from France? Is it a French word?
Yes, it's a French word. It's a
Yeah.
French word, yes.
It means friend, compagnon, a colleague or friend, and this is a you know the friend classes maybe in C++ or this is some simple thing like it is a friend, and friends have access to private members, and that's why this companion keyword comes here into this world later. So it means it's a object, but it's a friend. This object, a companion object, and the companion object is more static object, and this kind here is a inner object in this class A. We have access to this object. So the next question is, have we access from outer? We don't have access from outer. No? Outside A is not accessible, but I think the companion one is. The companion one could be accessible. No, it's not. At the moment, it's not really accessible. But maybe from A, D, yeah, now it's accessible to this companion because it's static. If we write this companion here, we have a static access to this object inside this class. So this is a real, it is a real object in memory, and this is some static object in this class, and we can access it directly. So we have static members here because in Kotlin you don't have the keyword static. So this is wrong. In Java we know static, in C++ we know static too. In Kotlin we don't have any static variables, but we have companion objects, and if I leave it out the name, it is a anonymous object. And how to access the number? Now I can access the number, the static number. This is now a static attribute. Num is now a static attribute in class A. The Kotlin compiler generates Java code, and this Java code is then a static attribute in this class A. So we have now the solution for maybe how to create static members. Use companion objects, and if they are anonymous, like this one, you can have direct access to the parts inside. If I leave the companion word out, this object only exists inside an object of A, and it has to have a name. It has to have a name, or I give it a name like this. So I have to give it a name for accessing, and I can't access it from outside. I can't access it over the class name, and you see I can't access the interior object. I have only this object in this variable C, but I can't access this value at the moment. So better to have the name here and give it this name. Now I can access it again, and from the class to build an object, and over the object I can access now this number, but it's not public. You see, I can't come from outside, it's private. Can't come from outside, it's private. From inside I can access it. From outside, not accessible. Okay, the object expression. Normally you want to derive, so this is in case of derivation. You have the possibility to derive interfaces, implement them here, and bring work inside this class body. This is the idea. you override some functions, and those functions are then callable with the objects. Good. The next thing were inner classes. Let's come to inner classes. In Java, we just write a class in a class. So I leave this out again. We focus now on inner classes. We want to have a class B existing in class A. In Java, we write just class B and say this is a class in the class A. But what do we get if we have B objects here? What do we get if we have B objects here? Let's have a look. So it's a class A and B, but for inner classes and access to the outer classes, I could have a toString method for this type B2. Let's make a toString method, and let's try to access some things from class A. Let's try to give the surname. So this is now not correct. Okay, maybe some braces here. So we have no access to this surname. Normally we have access to the outer class, but we have to annotate it with inner class. So this gives us access to the outer class, and if we don't have access to the outer class, this class is standalone. Now it is standalone. It is inner class. You see this here. It is $B. That's why B is just existent in the class A. Nobody can create objects of type B outside from A, but they are standalone. So I don't need the class A, an object of type A existing. So there is not the need that an object of type A is existing outside class B. And if I annotate it, or if I write the keyword inner, now an object of class A has to exist. And they are in this nested connection. If the object of class A has to exist, I can access the memory, the properties. And if they are decoupled, now they are decoupled, I can have a B class object without an existent A class object. Let's see how to create Bs. I can create a B like this. Now, without an existing object of type A. This is now the case. So we have no access to the surname from A, but we could use we could access companion objects. Those are static, and class-wide static things we can access without the existence of an object of type A. That's why we have access to everything everything outside of B what is static, so just the companion objects. Okay, and if we want to connect it like we know it from Java, this is the normal approach in Java. We have them connected. B only exists when within an A. Now this is an error. We first have to create an object of type A, and inside the object of type A we can create the object of type B now. Have you any questions? Then the next idea is how to access attributes which are called or named in the same manner, so have the same name. and are of the same type. They could be of another type. So how to access this one? If I give the surname out, which surname do I get? So I get this one. You see it. You see it. The compiler, the IntelliJ IDEA sees it as well. So if I give the string surname, he says, oh, nobody accessed this property. But if I do the $sign here, the IDEA recognizes, okay, now the property here is actually accessed. So we know already this surname is of this scope. If we want to get out this scope, we have to write the class name of the outer class. So we should write a, in Java we would write a point surname. But this is not right here. Okay, we forgot the curly braces. Make it. But it's still not right. So what we need is this approach, but we have to write it something other. We write it like this. Moment. I thought we write it like this. Moment, why not? We have to write. We write the A before. Maybe we write the A before. Let's try the A at here. Now it right. Yeah. Just write it so. We use the at sign in case not the point. The point is access a static member. This is no static member, so we write a at sign. Because this is a label, and this is the label for the scope. So if we have a new scope, a class's scope, we get automatically a label for this scope, And we have two different this pointers. We could use this pointer as well. And for this is a surname. Let's try. So we get 0 in this label is redundant because it cannot be referenced. Okay. This, we should write this at A. Now. How is it now? Now it is really. Now it's working. So this at A. We have to write this at A. If we just use this, we have this at B. This is the reference to the actual object, but in the B scope, in this scope, this is the normal approach if we leave this B, if we leave it out. So we become this from the scope here. And if we want to access the outer part of the object in the A part, we should write this at A, because we get a label for this block. And we access it with at after the this reference. Now we have here the word utter in the surname because it comes from the surname here and is a string, and if we use it from B or from this without anything or without this as well, then we have it from here and is an integer number called surname and is 0. So this is a little bit different to Java, but not that different. We would have a dot this. In Java we would write a dot this dot surname, and this is not correct here. So we have this at A as annotation to use this label. And then the idea again sees it's not used this surname, so we could append it again with this expression. Then we use both. So, have you questions to this approach? Okay, then were the members. We have seen we can have constructors and initializers. Okay, let's make another function, but we have a function here. It's defined to string, so a overridden function, and we use it if we print it out. The object is the same way like Java does, because this is a function from a Java object, from the class, the object class, formerly known in Java. Now let's come to inheritance. And inheritance is a little bit other than we know it from Java. At first, we have a new base class for all classes. In Java, all objects derived from object, but not the primitive types. And that's why in Kotlin we have a class above the object class. So the object is derived from the any class or the any type. Any object in Kotlin is, or any thing in Kotlin is a object. Any type is derived from any type. This is interesting because we solve it and we are compatible with Java. We build up the extension tree and make a new root. This is the new root of the extension tree in Kotlin. But directly under any we have object, and all other objects we create are as well derived from object. So it's just a special constellation to have the primitive types, real object types as well. So all have capital letters in front and begin with a capital letter in their name, int, double, float, character as well. So this is the normal stuff. So all classes inherit from any. A parent class must indicate inheritance. This is new. So in the normal object-oriented languages, there's mostly possible to derive from almost every class, except in Java, except of final classes. So if I want to stop derivation from a class, if I say okay, from this class is complete, nobody can extend it and use the polymorphism to bring in new methods, we can say this class is final. We declare a class in Java as final, and then it is not able to derive. If we do not annotate the keyword final into our class declaration, we can inherit and so on. And here in Kotlin we have a little other approach. We have to write the keyword if we want to have extensions or derivation. If we want to allow a derived class from our base class, we have to open it. And if we don't open it, it is closed. Maybe you know this open-closed principle, and there this keyword is coming from. So it's open or closed, and without open it's closed. So all classes are automatically closed. You may not derive from your class if you don't open it for derivation. If you open a base class, you can derive, and for this you just need this colon and say which class it is derived from. Okay, we have a class A, and the inner class we leave it out again. We have our class A with our John Utter, and maybe we derive this attribute. We make a class A, just has one name in the Middle Ages, and then we have a version B, and this B should be derived from A. To make it possible, we have to open up the class A. The class A is now open, and B can derive from A, but if I construct an object of type B, I have to construct an object of type A first. So we have this super keyword in Java, but we do not have it here. Since all constructors, if we have more than one, so if we have secondary ones, if there are several constructors, they delegate to the primary one. So all constructors are safe, they delegate to the primary constructor, and I have at least a primary constructor, or how to say. So if my base class has a special constructor, like my class A has, or I go back, let's go back. I take open class A, and then I can have class B constructing an A. I have to say how to construct an A. If you construct a B, if I want to construct object of type B, I have to clear out how to construct the base part of this object. And that's why I need constructor here. So this is a constructor from the A object. If I have my A object like this one, I would say construct the A with Joe or construct the A with Mary. So if I use class B, I always get A with. So maybe we have this funny overridden function to string again with the name in it. And as you already know, the B object is derived from A. We construct the A part with the string Mary if you don't give anything else here. And in B we can't give anything else. So I cannot give the a keyword here. So B has actually no special construct accepting strings. So we should do it here and say, okay, we have a name which is a string here called maybe Mark or Joe, John, what we want to have. So, but here in this case, here is just Mary inside. So we want to let's do it away. So we want to have a name. And this should be Mary if we don't give anything, and if we give anything, it could be something else. Name string. No, this is the name in the primary constructor of class A. In this way. Other constructors should delegate to the primary one. The primary constructor is now the constructor from A. You see this? This is the primary constructor from A, and it is also the primary constructor from B. Other constructors have to delegate to this primary constructor. We can now have a string name again, maybe with Mary here. Leave this out. Then we have to wait. Yeah, we need a primary constructor, so come on. This name. Oh, what's next? What's up now? So B is constructed with this primary constructor. We need it, actually. But this is the primary constructor of B as well. No, it's not as well. We have it here. So this is the primary constructor of B. I'm a little bit confused. So that's the primary one of B, and this is the primary one of A. I can use a name string here. This is Mary, and then we can have Mary here. Now it is like I want to define it. The primary constructor of B delegates to the primary constructor. You see, this is the same code like the secondary constructor is delegating the primary one. If I have a secondary constructor delegating the primary one, then it goes like this. And you see this code here is the colon followed by the name of the constructor, in this form this pointer here, and in the other form it's the name of the constructor of the base class with the parameters. So it's the same code. It's compatible, I think. So now it's more better to understand. We have this arguments, this primary constructor for B, and delegate to the primary constructor from A. Since A has a primary constructor, we have to use it. And we can give the name into this one. In Java we would write super. So in Java we would have written constructor, and the first thing we do would be super. But here we have no super. This case is already done for us since we do a primary constructor from A, since we call this here. Okay, the braces, I don't need the braces. Now let's give B a surname. So we could say, okay, we have new parameter, and it's the value surname, also a string, and it's called other. So the B version of my overridden function should be, and we can't override it now. You see this? It's not open in A. Yeah, it's not open in A, so we should open this function for derivation here too. And give it the value of surname and the return value of the base version of this function. So maybe we use a toString. In Java we would write a toString, but here we don't have a toString to call, so we just have this at a toString. No? Do we have a super? No, we don't have a super. Yeah, okay, we have a super. Actually, super toString is the base version, like we know this, and the other part could be then the surname. Now the object of type B is giving us both the name and surname through derivation. We have to open not only the class, we have to open the methods as well. So if we open the class, this method is automatically open, but if we don't open the class, the method has to be open. And So same thing for the values. If I have a value x, type of int with the value 0, to redefine it, I have to open it. This fun is already open in the base class, and we can use it. But if I want to have the value x here, it is not allowed. It hides the supertype. We should have override maybe, and therefore we must open this attribute. Now we can override this x, and we have two versions of x. We have the x with a 0 value from the supertype, and x with value 1 from the derived type, which looks like this. In our toString variant, we could append now the super x and the x. Now we have access to all those attributes, but they have to be open. And normally functions have to be open as well. So this is for redefining the functions. This should be open as well. Okay, let's make another function. Fun. Get a value and it delivers 1. Write this function get value here, and it delivers -1. We must override it, open it. So in this example, this function was open for everybody because it's open in the object class, and then we can derive. But this function has to be open for polymorphism. We have to open it. We have to open the attributes for function, and we have to open the functions for redefinition. Classes, attributes, and functions have to be explicitly opened for. That's what we have to do, to think about. We have to explicitly open it up, and in Java we have to explicitly close them with a final keyword. But here we have to explicitly open them, then we can derive with the override keyword. Derive from opened members, classes and members, with colon in case of classes, or the override keyword. That's how it works in Kotlin. And especially the combination, I have to call the super constructor if I derive, and the base class has a primary constructor, then I have to use it. This is cleared automatically, so the primary constructor here has to delegate, and this is the same code as we write for delegating a secondary constructor to the primary constructor. This is very interesting. Yeah. but it's the same. We delegate here automatically behind the scenes to the super constructor. So it's write it once, get two things. Get derivation derived from the base class and call the super constructor in this. Is done in this small piece of code here. Really interesting. Have you questions for that? The keyword final also exists, so we could have a thing final and then overriding is not allowed. We can open it up and then it is open for derivation, and if we want to stop derivation, we write the final keyword as we know it from Java. So stop further derivation with the final keyword. So now let's try to open this final class, and this will not work. So finally open or open final can't be on the same line. It makes no sense. Yeah. Either make it not open, so leave both, or write only any one of them. But if I want to have it final, I don't have to open it. So this is obsolete. In my case, I wanted to open it to rewrite it. Okay, and the polymorphism is then working here. Maybe we can use super get value -1, and then it delivers -1, 0, 0. Okay, and in case of A is the most simple class. We haven't changed anything. We just have the name here into the toString version, and in the B version we have all the accessed values, so the derived values and the base values as well. So everything should be clear in case of derivation between two classes. So we're almost at the end. Let's have a look on the next slide. We already cleared out the most things. So this is a thing we have cleared out. Access to the outer class with super add. Class name is possible. Super add class name we can access to the outer class. Did we do it? We had super this one, but we can say super add A as no super add A. Why not? But it was like this. Super add A should access the outer class too. Why it does not? Okay, maybe I should reread why I have written it down. I don't have an example here, but yes, I have a special example. Moment. Super add and the class name, and then we can access the base class. That's right. Let's try to do it again. Super add A should access the base class and make it callable. But maybe they have changed something in the version, because I learned with version 1.2 from Kotlin, and now we have version 1.4. So I'm not sure, because we have super here with a point, and if I write at, it is not allowed. I have super at B, I can write super at B, but I can't write super at A. So Okay, this is in the inner classes. Okay, moment. In the inner classes. If I have a inner class, then I have this approach. And we have just super at B. But if I write a inner class again, so that's why I have super at inner classes. So I need an inner class. This is why it is here. In inner classes, we can write super at as we had before. Inner class C. In my class B, I can write super add A and access the things from A. Normally. Why not? Because I need an object already. It's unresolved, this reference, because I need an object of this inner class. So I should have a fun C is super add A now. No. Super at B. Yeah, the super at B is the super type from B. There is never a super at A. It's the super type from B is A. So we are in the inner class, but we can access the super things from class B if we have super at B. So the super keyword is just working with one step to the base. As in Java 2, we can go one step forward from class B to the base class and not more. So that's why I just have super at B. If I'm in the class C, I have access to this label from the class B, and I could use this label for class C or class B. Both have a toString approach. Yeah, both have a toString method. This is the standard generated toString method, and this is the method I have overridden here down here. Okay, so this is a small example therefore. And now we are at the end. Next week we go on with abstract classes and maybe some static methods too. In this companion object therefore again, and then we make property getters and setters, classes, objects and interfaces. Yeah, and some specialties. Okay, fine. Now we have almost made 5 minutes longer than we should have, so I give you 15 minutes break. We start over 11:35 with the Android part of our lecture. I thank you very much, and we see us after the break.
Thank you, Professor.
Thank you too.